Hey everyone, and welcome. If you've got a physics exam breathing down your neck, you have come to the perfect place. We're about to do a super fast run-through of the most critical concepts from past exam papers. Our goal? To turn that confusion into confidence in just about 5 minutes. So you ready? Let's get right into it.
You know that feeling when your head starts to spin trying to keep all these similar-sounding terms straight? Forced versus damped, resistivity versus resistance. Yeah, it's a classic problem. But don't worry, that's exactly why we're here. We are going to make these differences crystal clear, so you can walk into that exam knowing precisely what's what.
All right, let's kick things off with sound. Everything about sound starts with vibrations, and really understanding the 3 main types is the foundation for so many exam questions.
Okay, so check out this breakdown. Free vibrations, they have no outside force, so in a perfect vacuum, their amplitude stays constant. Damped vibrations are what happen in the real world. Think of a swing slowing down. The amplitude gets smaller over time. But forced vibrations, that's the one to watch. An external force keeps pushing it so the amplitude stays constant. Seriously, just look at that external force column. That's the dead giveaway right there.
And this brings us to a super important special case of forced vibrations, resonance. You can think of it like hitting a power-up in a video game. When the frequency of that external push perfectly matches the object's own natural rhythm, the amplitude goes through the roof. This is a massive concept, so really make sure you get this one locked in.
So let's talk about the sound wave itself. 2 of the most common points of confusion are loudness and pitch, but it's actually really simple when you break it down. Loudness is all about amplitude, how tall the wave is. Taller wave, louder sound. Pitch, which is how high or low a note sounds, depends only on frequency, how packed together the waves are. That's it.
So, if a flute and a piano both play the exact same note, they have the same pitch, right? Which means they have the same frequency. So why do they sound so completely different? Well, that's where quality or timbre comes in. It's all about the unique shape of the waveform that each instrument makes. It's pretty cool, right? Different shapes create all the rich sounds we hear.
Okay, let's switch gears completely. We're jumping from the world of sound waves to the flow of electrons. It's time to crack the code of electricity, and it all begins with one single law that governs pretty much every circuit.
Ohm's law. You've probably seen V equals IR a million times, and for a very good reason. It's the simple, powerful heart of electronics. Think of it like this. Voltage is the push, current is the flow of electrons, and resistance is the pushback. If you can get your head around that simple relationship, you're already halfway to solving most circuit problems.
So what is this resistance really? Well, it's exactly what it sounds like, opposition to the current. You can just think of it as electrical friction. And the important thing to remember is that 4 things can change it. How long the wire is, how thick it is, what it's made of, and how hot it is.
But here's the classic trip-up, telling the difference between resistance and resistivity. Resistivity is what we call an intrinsic property. It's like a material's unique fingerprint. Copper has a certain resistivity, and it doesn't matter if it's a long, skinny wire or a short, fat block. The resistivity of the copper itself doesn't change.
Let's just look at this visually for a second. See? Both of them depend on the material and the temperature, but only resistance, the total opposition, cares about the length and area of the wire. This distinction, I can almost guarantee you'll see a question on it.
Okay, let's put this to the test with a classic exam problem. Imagine you've just got a regular wire, and we'll say its resistance is R.
Now you take that wire and you stretch it. You pull it until it's twice as long as it was before. Now here's the key part. You haven't added or removed any material, so the volume is the same. That means if it gets longer, it has to get thinner, so its area gets cut in half.
So here's the million-dollar question. What is the new resistance of this longer, thinner wire? And don't forget the hint. The material is still the same, so its resistivity hasn't changed one bit. What do you think?
The answer is 4R. It becomes 4 times bigger. Now why? Well, think it through. Resistance is proportional to length, so when you doubled the length, you multiplied the resistance by 2. But it's also inversely proportional to the area. So when you cut the area in half, you multiplied the resistance by 2 again. So 2 times 2 gives you 4. This is a great shortcut to remember for your exam.
For our final big topic, we're going to take a quick journey across the whole electromagnetic spectrum. We'll start with the highest energy waves and work our way down to the lowest.
Kicking things off at the super high energy end, we've got gamma rays. These are the heavy hitters. They come from radioactive decay and have so much energy they can pass through almost anything. That's why we can use them for really powerful stuff, like treating cancer or sterilizing medical tools.
Taking one step down in energy, we find the very familiar X-ray. You know the deal with these. They go through your skin and muscle but get stopped by your bones. And that, of course, is what makes them perfect for spotting fractures and for all kinds of medical imaging.
Next up is ultraviolet light, or UV, which we all know from the sun. It's got enough energy to be chemically active, which is useful for things like sterilization. Fun fact, it's also what makes things glow under a blacklight, which is how it's used to spot fake money.
All right, now we're crossing over into the lower energy half of the spectrum with infrared, or IR. When you think infrared, just think heat. Every warm object, including you, gives off infrared radiation. This is the magic behind thermal cameras, night vision goggles, and even your TV remote.
And finally, bringing up the rear with the longest wavelengths and the lowest energy, we have microwaves and radio waves. I mean, these are the absolute workhorses of modern communication. They power our Wi-Fi, our cell phones, TV, and radio broadcasts, basically almost all the tech we use every day.
Whew, okay, that was a lot of information, really fast. So let's just boil it all down into one final cheat sheet. These are the absolute must-know takeaways for your exam.
Ready? Let's lock these in. For sound, loudness is amplitude, pitch is frequency, quality is waveform. For circuits, resistance depends on the wire shape. Resistivity is just about the material. The wire stretch problem, doubling the length makes the resistance 4R. And for the spectrum, gamma rays are the most powerful, radio waves are the least. Burn these into your brain and you're going to be in great shape.
And that's your 5-minute refresher. Now go out there and absolutely nail that exam. If you found this quick breakdown helpful and want more, do us a huge favor and subscribe to the Study Slide YouTube channel. Good luck!